sent that particular image if I'd realized it would have been shown at the beginning of the talk so people could compare it with the reality and see the difference in hair color, but there you have it. With an apology to Professor Myrna Ott, my college speech teacher, who posted her 10 cardinal rules of public speaking, rule number 8 was, never begin a speech with an apology. When Lisa Johnson asked me if I would consider giving a talk at this C-STAR lecture series to discuss methods of statistical inference, my first response was that I doubted I had anything to say that the attendees did not already know. Further, I'm a quantitative methodologist in educational psychology who knows next to nothing about aphasia treatments. Nonetheless, her persistence, combined with my admiration for students in your department who enroll in my courses, held sway. Your students are consistently among the top achievers in my courses, so kudos to the faculty for how you select and develop your students. They're great, so I accepted the invitation. Now that I have looked at the list of distinguished speakers in this series, individuals who discuss cutting-edge topics in your discipline, I again question whether I belong here. I'm clearly an outlier. Therefore, I'm going to break Professor Ott's 8th rule of public speaking. I apologize in advance for discussing methods that are not cutting edge, but that have been dominant in your discipline and mine for many years. Now that said, I offer this hopeful pebble. I will attempt to speak of old methods in new ways, not to say it differently, but to provoke thought and discussion about such methods, specifically to reconsider where we put the emphasis when we report research results. I have no desire to waste anyone's time, so I've set 3 goals. First, I want to provide an opportunity to reflect on how the philosophical girders of our statistical methods align with our research practice. I ask, is our methodological practice consistent with our beliefs about scientific progress, and could we benefit from any tweaks to this practice? In short, can we do better? My second goal is to provide some new ways of thinking about inference and methods. I hope that everyone will come away with at least one, that's interesting, moment. Finally, I remind myself that the VIPs in attendance today are students at this university. You are still developing your scientific philosophy and building your methodological toolboxes, so my third goal is to provide you and others early in their career with some additional ideas as you continue your journey. You sit alongside experienced and distinguished researchers who are already well versed in my topic, but they'll indulge me if they know that you benefit from our time together. As I prepared these remarks, I decided to make you my primary audience, so thank you for this opportunity. Let me establish 2 conditions for my remarks. One is required to maintain the accuracy of my claims. The other is a choice I've made, both to facilitate the communication of ideas and to broaden audience participation in thinking about these ideas. The required condition is to adopt a frequentist approach to probability. The 2 most common probability definitions employed in the research of our discipline are frequentist and Bayesian. The frequentist view is that probability is an a priori expectation of, as the name suggests, the frequency of observing a specified event in a long-run sequence of trials with a defined event space. For example, if one was to randomly toss a 6-sided die with face values from 1 to 6, prior to tossing the die, we would say that the probability of observing a 6 on our toss is 1/6, or about 17%. We reach this calculation by imagining what would happen if we toss the die 1,000,000 times, then count up the number of trials in which we observed a 6, and divide by 1,000,000 to arrive at 17%. Importantly, the percentage obtained after 1,000,000 rolls is not a probability. It is an observed event frequency to experimental trial ratio. We do not need to think about probability for past trials. We have the data in hand. Probability is a priori, or before the fact. What we can do is use this information to talk about the probability that we'll observe a 6 the next time we roll the die. The Bayesian view of probability is not based on long-term frequencies, but is a statement of expectation or personal belief, and this probability can be changed after observing additional data. Imagine a closed box with a hole in the side, large enough to put your hand through. Pick up a 6-sided die, put your hand through the hole, then roll the die. Before you open the box, I ask, what's the probability that a 6 is face up? If you're a frequentist, you should answer 0 or 1. You either rolled a 6 or you did not. The event is over. By contrast, after the roll and before opening the box, a Bayesian can correctly state the probability that the face up on the die is about 17%. The frequentist is focused on the truth state of the statement that the die is showing a 6. The Bayesian is focused on quantifying our personal understanding based on current conditions. So it is acceptable to have a truth value within the range of 0 to 1. The Bayesian approach to probability is powerful. Many argue it is better suited for inference in our flavor of science. Yet the frequentist approach continues to dominate the initial training in statistical inference in many disciplines at most universities. This is one reason my remarks are based on infrequentist probability. The other being, I was trained in this classical approach, and I'm not qualified to represent the thinking of a Bayesian statistician. The second condition for these remarks, this one not necessary but my choice, is to assume throughout the simplest of research designs a one-factor, two-condition study in which the units of one condition serve as the control and those in the other receive a treatment. This simplifies my presentation and also allows us to bring on board those who may have just begun their foray into statistical inference. Also, this approach does not restrict my conclusions. We could consider designs with multiple factors and covariates using constructs yielding observations obtained through many measures. My primary objectives would remain the same. The focus is not on the design per se, but on a general set of propositions I hope will at least provoke thought and discussion as we reflect on the current practice. Here is the equation for a well-known physical law. It is the law of gravity. F is the gravitational force on two objects. The masses of these objects are m1 and m2. The distance between the centers of the two objects is denoted r. Finally, g is the gravitational constant, 6.674 times 10 to the negative 11 meters cubed per kilogram per second squared. This gravitational constant is also known as the universal gravitational constant because it applies to any two objects anywhere in the universe at any time. It's why we call it the law of gravity. With this equation, we can measure the force among the Earth and the Moon. We can measure the force among our galaxy, the Milky Way, and our nearest large galactic neighbor, Andromeda. We can measure the force the Earth is applying to each one of us, and the equal force we're applying back to the Earth. We can also use this universal law to provide a numerical quantity for the attraction among the hearts of two lovers in an embrace. These calculations will yield the same result today, tomorrow, and next year. The unchanging nature of this law results in greater understanding that in turn sets the stage for work in astronomy and aeronautics. It is used in the calculations of engineers. Understanding leads to control, and the ability to control is the goal of our disciplines. It is why we in the behavioral, social, and medical sciences have developed lines of research that mimic the older scientific traditions established in the physical sciences. If we can uncover laws, it will lead to greater understanding. Beyond that, it will give us more control, and more control means stronger therapies, higher educational achievement, more effective social policies. Here is an equation for relating therapeutic outcomes to two types of therapies. I will designate one as the control and one as the treatment. Though both conditions provide a therapy, our interest is in determining the effectiveness of the treatment relative to the control. Y is the observed score of an individual who has received one of the therapies. For this example, we can assume without loss of generality that higher values of Y represent a more desirable state of affairs. Through such techniques as taking baseline measures or selecting study participants exhibiting similar degrees of the pathology, we can associate higher scores with better therapeutic outcomes. X is a Bernoulli variable, the simplest of all types of variables. It only assumes values of 0 and 1. In our equation, it serves as a therapeutic indicator when we assign values of 0 to those who receive the control therapy and 1 to those who receive the treatment. The value of mu provides the control group baseline, as we can easily see by setting x equal to 0, So we end up with the equation y equals mu. Our primary interest is in determining the value of beta, for this is a measure of the effectiveness of the treatment relative to the control. Here's a very simple example. The observed scores for the control are 3, 4, and 5. Those for the treatment are 13, 14, and 15. We create a linear model with a control baseline of 4 units and then measure the treatment effectiveness as 10 units on whatever scale we are using for assessing outcomes. Let us return to the law of gravity and put it side by side with our therapeutic effectiveness equation for the purpose of determining the differences among how we use these two equations. In the first equation, we use the scores of 2 participants, that is, 2 masses, to calculate the outcome of the force. In the second equation, both our baseline and our effectiveness measure are not values of the participants themselves, but rather are indices to represent the individuals in each condition. The first is the control group mean, the second is the average treatment effect. So difference number 1 with physical law is that the values we obtain in our equation for both therapies do not rely on a single participant, but rather on indices, the means, to represent collections of participants. We should indicate that we are using group indices rather than a separate effect for each participant. We can slightly modify the equation to make this explicit. Here, J can be 0 or 1 to indicate control or treatment condition. Given that we're now indexing condition membership, I also switched from C to 0 to subscript the control mean. Now our outcome, Yj, is a condition mean, but we wish to determine the outcome for an individual in our study. We need a further adjustment to our equation. I've made 2 changes now. First, I included a subscript for a clinical participant, person I in condition J. Second, I added a term, epsilon, that indicates the degree of inconsistency of the participant's outcome with the outcome index, the mean, of that specific therapy condition. Here's the second difference between our equation and the physical law. In our equation, an observed outcome depends on both the therapy condition and other elements that are not part of the therapy. These elements are the consequence of working with living organisms. We can say quite literally that while beta is the science, epsilon is the soul of the equation. In the study of the physical world, the scientist can focus on the characteristics of interest while controlling those characteristics that are peripheral to the study. There's no epsilon. In the study of living organisms, most especially human organisms, epsilon can take many forms. It can represent anatomical and physiological differences. It is influenced by a patient's effort, a student's motivation, a participant's attitude. It reflects the relationship among the clinician and the client. It can change with the environment and the time of day. It depends on the quality and quantity of sleep, nutrition, and exercise. It is moody. It is also susceptible to variations in treatment implementation, potentially changing values with the change of therapist. In short, while we can experience success akin to that of the physical scientists in manipulating what is behind X in order to change beta, controlling epsilon becomes a feeble cry in the vastness of a universe of extraneous variables, most of which we will not even consider if we make a futile attempt to list them all. This presents a problem. With Y, our observed outcome on the left side of the equation, and both beta and epsilon on the right side of the equation, how are we to know the relative contribution of these 2 parameters to what we observe? That is, how can we verify treatment cause? In my own work, we primarily rely on either the Pearl or Rubin causal models. I'm going to focus here on the better-known causal model proposed by Donald Rubin. This model has undergirded research endeavors in our disciplines, yours and mine, for many decades. The model proposes to address the influence of epsilon through experimental design, so in a moment I need to consider the role of experimental design. But first, there's a related detail we need to consider, and it's of great importance. Consider again the law of gravity. How does the scientist determine G, the gravitational constant? She measures the mass of the first object, the mass of the second object, the distance between them, and the force that's being exerted, and with some simple algebra, she then has an equation for G. With our model, solving for the unknown of most interest looks like this. We can observe Y, our outcome measure. We can determine X, our indicator telling us whether a study participant is in the control or treatment condition. But we still have two unknowns: mu, the effect of being in the control, and epsilon, the value reflecting the individual soul of the participant. So this assumes a perfect observation, and that is, we have measured the participant's outcome precisely, and that's not going to happen either. So not only does epsilon reflect motivation, attitude, nutrition, and a host of other attributes, both known and unknown, but we also pack in with it the error of our measurement. Soft science is hard. The standard way to address the epsilon dilemma involves 3 steps. First, we remove it and return to our original model. This time I have left the I subscript on the left-hand side of the equation, indicating we're going to make observations of the individual, but I've eliminated individual characteristics on the right side. In essence, in this first step, we're treating all participants within a specified condition as clones. Heart and soul are gone. Our primary focus is on the group as a whole rather than on the individual. How do we justify this when we make our observations and obtain different scores for different participants within the same condition? That's not very clone-like. This leads to the second step. We hide under a hat, like this. This is an implicit recognition that there are other variables in play and there is imperfect measurement. In short, for the moment, we set epsilon aside but admit that it exists. Thus, we estimate the control baseline and the treatment effect. From this, we can estimate what the observation for our participant would be if we could perfectly measure and completely control extraneous human behaviors. From this, we will obtain the same score for every person within a condition. Yet, despite this calloused approach in the name of science, we cannot help but recognize individual differences. In progress. So we take a third step. Here it is. So here's our third step. Presentation. Soul is back. As with the other 2 parameters, we recognize it as an unknown, so we estimate and give this estimate a name, residual. The residual puts humanity back into our science. Indeed, the analysis of residuals should be rich territory for our science. Most of the time when I hear the term residual analysis, it is a reference to constructing graphs, calculating statistics of residuals for the purpose of evaluating the validity of statistical inference. Are the residuals normally distributed? Are they homoscedastic? Do they suggest autocorrelation? And so forth. These are important questions that need to be addressed, but I'm using the term in a different sense. While the model provides estimates for what we are studying, the residual may suggest what we should be studying. Why was the treatment twice as effective for 6 of our participants as it was for others? Why are participants 12 and 19 not responding to the treatment? Why are residuals slightly higher for one clinician than they are for another? The model references the group, the residual references the individual, and we can learn from both. Putting it all together, here's our revised model. I'm now prepared to offer 2 definitions. Soft science is distinguished from the physical sciences by 3 characteristics. Models put the focus on the group as the primary unit. Models include epsilon to account for individual differences, and the parameters of each model wear hats. They are estimated. Inference is a systematic and logical attempt to remove the hats. The basic ideas for how to remove hats are the same in every introductory statistics textbook that I have seen. They are based on random process, specifically a simple random sample. This sample can be conceived of as one of all possible random samples. Our single sample provides the statistics for our study, but we also conceive of hypothetically calculating statistics from all possible samples to construct a sampling distribution. By finding where a statistic fits on the sampling distribution, we can calculate what proportion of the statistics in the distribution are below or above our statistic. Of course, constructing the sampling distribution requires knowing the parameter of the distribution, so we hypothesize one, like this. It's most common to set H to 0. Consider the possibility that this guess is wrong. Indeed, in the soft sciences, we want it to be wrong. We want a treatment effect, so we add another possibility. We can now test the null hypothesis of interest, comparing it to an alternative hypothesis that we hope wins the day. We compare our statistic to the universe of possibilities for this statistic as manifested in the sampling distribution. We make a decision that will keep our type 1 error rate, that is rejecting the null hypothesis when it is true, at a low level such as 0.05, consistent with the industry standard. Thus, when we obtain a statistic that is above some critical value on a probability distribution, we reject the null hypothesis. We recognize we may have made a type 1 error, yet we set up our study so the chance of this happening would be akin to winning the raffle. Possible, but not likely. Now, if we set aside the publication value of this finding and focus instead on the scientific value, we may encounter a matter of some concern. Everything we've just done is based on selecting a random sample from the population of interest. Really? A sample composed of individuals selected at random from the entire population? Is there even a grant available to fund such an endeavor? I've never seen one. Yet what is ubiquitously taught in Stats 101 is assume you have selected a random sample. Bring in the Rubin causal model. In brief, instead of using random samples, we will incorporate random assignment into our design. What is not commonly taught in Statistics 101 is that such randomization can also be used to create a sampling distribution. Instead of statistics calculated from many simple random samples, we can calculate statistics from many randomizations. Just as we have a population of units, we have a population of potential randomizations for any set of individuals we wish to study. And now some serendipity. It can be shown that using the mathematical models we employ for random samples will provide a fairly accurate approximation to the exact probabilities we can calculate from a sampling distribution of all possible randomizations. Random sampling or randomization, or both, will provide us a means of calculating probabilities associated with testing hypotheses. Though different random processes may lead to similar probability calculations, they do not lead to the same conclusions. We can envision 4 random process possibilities that lead to 4 types of inference. First, we could employ both a random sample from the population and randomize the member of this sample to the treatment and control conditions. We are unlikely to achieve this feat during our research careers, but the idea of it still makes us giggle. This would lead to general causal inference, in which we both attribute cause to the treatment and extend this cause beyond our study to the target population. If we could randomly sample but have no control over who receives the treatment, the result is population inference. An inference to the population, but one for which we cannot make causal attribution. If, however, we cannot obtain a random sample but can randomize to conditions, we can infer the treatment as the cause of improved outcomes for our participants. That is, we can make a specific causal inference. Finally, if we can neither randomly sample or randomize so that we have not met either of the conditions necessary for calculating probabilities to test hypotheses, I believe there's still merit in conducting such tests. We could call this calibration inference. Think of it as a means to curb our enthusiasm for declaring desired outcomes, even if there's little evidence to support such a declaration. A final note on randomization. On multiple occasions, I have heard or read the statement that we randomize to conditions in order to equate extraneous variables for control and treatment participants. If this were true, there would be no need to include probability calculations in our analysis. Mean differences would imply a treatment effect. It's not so. It is true that such extraneous variables are negated in the long run, that is, across all possible randomizations of the participants, but we've selected one from the population of randomizations. The purpose of randomizing is not to equate, but to remove systematic bias so we can calculate probabilities conditioned on the truth of a hypothesis, just as we rely on random samples to remove sampling bias, again, so we can make reasonable probability calculations. Here again is our working model. I have defined inference as the systematic and logical attempt to remove the hats. These hats are a recognition that if we randomly select from the universe of possibilities, be they participants or randomizations, each selection will result in a different estimate of our parameters. The implication is that hat removal must be tied to probability. Whereas the laws of the hard sciences are deterministic and yield consistent results across experiments, the laws of the soft sciences are stochastic and must accommodate a degree of uncertainty. Now, the traditional tool for expressing uncertainty is the p-value. This value continues to be a cornerstone of statistical inference, but with widespread use has come substantial misunderstanding and misinterpretation, as documented by studies of research practice for over 30 years. Most incorrect interpretations fit into one of what Rex Klein has referred to as the big five false beliefs. I'm not going to focus on misuse. Instead, I wish to discuss the characteristics of the p-value under the commonly accepted correct interpretation. Most methodology researchers express it like this. In words, P is the probability of obtaining the observed data given the truth in the null hypothesis. This is true as an a priori statement. That is, if we assume a true null hypothesis, then we can calculate the probability of making observations with values we specify in advance. The problem, however, is that's not how we do it. We calculate the p-value based on the data we've already observed. In frequentist language, the probability of observing data we've already observed is 100%. Thus, as Kuffner and Walker recently emphasized in The American Statistician, the p-value is not a probability. It is a statistic, just as the mean and standard deviation are statistics. After we have collected the data, we can calculate many statistics, and the p-value is among these. Now, there is a way to merge probability with p-values. It's done like this. The probability of making a type 1 error, that is a false rejection of a true null hypothesis, can be controlled at some level alpha if and only if we reject the null hypothesis when that p statistic is less than or equal to alpha. Now, perhaps this falls into the category of, well, duh. I ask you indulge me and consider the implications of a seemingly obvious statement. First, this must be an a priori probability statement because it necessitates we set alpha before collecting the data and calculating the p statistic from these data. We need to define the level of tolerance we have for type 1 errors, and this is captured in alpha. Second, we're performing what mathematicians would call a surjective mapping onto a binary codomain. Simply put, although our p statistic can assume any value in the inclusive range from 0 to 1, we will map these values onto one of two decisions: reject the null hypothesis or do not reject the null hypothesis. This will keep our type 1 error rate within our specified tolerance level. If we set alpha of 0.05 and observe p of 0.04 or 0.004 or 0.004, the decision's the same: reject the null hypothesis. Very early in my career, I had the opportunity to attend a lecture by Robert Rosenthal, a well-known psychologist who has studied self-fulfilling prophecies known as the Pygmalion effect, and also has co-authored some important statistical papers with Donald Rubin of the Rubin causal model. His lecture was a critique of statistical hypothesis testing, and while discussing our blind devotion to a specific type 1 error rate, usually 0.05, he said, "Surely God loves a p-value of 0.06 almost as much as 0.05. At the end, he invited questions. I stood up. I asked, perhaps God loves a p-value of 0.06 almost as much as 0.05, but what does she think about 0.07? I fear my point was lost on the audience, and perhaps even Professor Rosenthal, rightfully so, given it was a rather snarky question from a recent graduate posing as a wise guy. So now, years later, in a substantially more humble spirit founded in decades of learning how much I don't know, I'll return to the main point of my question. The idea that p equals 0.06 is almost as good as 0.05 has an appeal, but it ignores the reality that we only attach the p statistic to the probability of a type 1 error by setting alpha at a tolerance standard and mapping the p-statistic to a binary reject or retain domain using a decision rule. Maybe Professor Rosenthal was advocating for researchers to consider using 06 instead of 05 when setting this rule, but I don't think so. I'm convinced he was advocating us to consider that obtaining a P of 06 provides almost as much evidence of a treatment effect as 05. In other words, he was using the p-statistic as the effect size statistic, rather than as the input to a mapping rule that has a binary decision as an output. One evening recently, when my wife Jennifer and I were on a walk, we spotted a neighbor, and Jennifer said, "Morgan is very pregnant." My instinct was to mansplain that pregnancy is a binary variable, as evidenced by a reliable pregnancy test. Yet decades have passed since my smart mouth question to Robert Rosenthal, and with those decades has come, I would like to imagine, a degree of wisdom. So instead I replied, "Do you know when she's due?" Robert Rosenthal and Jennifer Young want what many of us want. Given the inherent uncertainty of our estimates represented by the hats on the terms in our models, we want to quantify both the treatment effect and the degree of certainty we can associate with that effect. This desire is both reasonable and reachable. To get there, we explore the inner workings of the p-statistic. The p-statistic is a composite of 3 elements. It is created from an estimate of the effect size, the standard error of that estimate, and a quantile of a mathematical distribution model. Let's put these elements together, but given our desire to highlight the main player, the size of our treatment effect, we'll separate it out from the other 2 like this. This defines an interval around our estimate of treatment effect. To illustrate, consider an instrument with a range from 0 to 100, where higher numbers are a desirable outcome. Suppose that our experimental outcome is that participants in the treatment condition manifested an average score 5 points higher than that of the participants in the control condition. Our interval might look something like this. The estimate of the effect size is clearly the main player here, sitting in the center of an interval whose width represents both the stability of our estimate and our error tolerance. We must select that tolerance prior to making our observations. This a priori activity is the same we employ for hypothesis testing. It gives us the probability that when we construct the interval, it will contain beta. Notice that beta on the axis wears no hat. Careful will now be tempted to say there is a 95% probability that beta is between 3.5 and 6.5. We must take out the word probability. This interval was constructed based on a set of observations. In frequentist language, the interval either contains beta or it does not. This is the same reasoning I employed with the p-statistic. It's not a probability because it is calculated from data. Now, statisticians have come up with a clever name for an interval that is constructed from our observations, but that includes an a priori decision. We call it a confidence interval. Imagine 20 cards randomly placed down in front of you, and you know that 19 of these are red and 1 of these is black. If your instructions are to select a red card, there's a 95% chance you will do so. Once you've slid a face down card in front of you, the probability is 0 or 100% you have selected a red card, yet you're 95% confident that you've done so. Given that p-statistics and confidence intervals are calculated from the same 3 elements, there should be a strong connection among a hypothesis test and a confidence interval. Yes, indeed. Consider again the following null hypothesis. This is general because I've replaced 0 with h. H can be any value we choose. And imagine this. Imagine putting in every value for h and testing all possible hypotheses. A confidence interval consists of all null hypotheses that are retained when we test all hypotheses using the observed data. The information we obtain from an interval is a function of estimate stability as manifested in the width of the interval. Narrower intervals provide more information about the parameter. The interval width is determined by a rather large list of study characteristics. Most of these can be addressed by researchers, so increasing the information obtained from an interval is within reach. Given the correspondence of hypothesis testing and confidence interval construction, is there anything to be gained by switching from a p-statistic to a confidence interval? Let me provide a few examples so you can judge for yourself. I will continue to use our 100-point observational scale. Now, here are p-statistics from 5 studies. How would you rank these in terms of your preference in your own studies? If you rank your preference from smallest to largest, that's reasonable. Without further context, that's what I would do. Let's use our hypothetical 100-point scale to provide some context. What kind of effect sizes might we observe? We could envision potential outcomes like this. I list some of the non-zero outcomes as trivial because some effects are too small to warrant attention. Just as the correlation among 2 unrelated variables will not be exactly 0, so might an ineffective treatment still provide some tiny indication of an effect, in addition to a range of trivial effect sizes. I've also chosen some arbitrary ranges to label as small, medium, and large. In real-world research, such labels would not be arbitrary, but would be anchored in theory and prior research findings. With this hypothetical scale, let us suppose the locations of these labels are reasonable, so as to provide more context for some examples. Let's take a look at 95% confidence intervals that correspond to those p-statistics I showed you. Underlying each example is R code that I use to calculate both the p-statistic and to construct the confidence interval from the same set of data. So the connection is real. Let's start with the very first, very small p-statistic, p less than 0.001. Here's the confidence interval. The dot represents the maximum likelihood estimate of the treatment effect. It is 6.8. So our best guess, based on the evidence of our experiment, is that the treatment causes a large change in the observed variable. We are 95% confident that across all randomizations, the average treatment effect will be somewhere between 5.8 and 7.8, as illustrated by the bounds of the interval. Note the interval separates 2 of the elements that are buried within the p-statistic, our estimate of the treatment effect and the stability of that estimate. Here's the next example. We still have a substantial treatment effect in our study, but now the bounds of our inference are so far apart that they include both trivial and large effects. Our estimate is unstable. The p-statistic is less than 0.05, consistent with our observation that 0 is not in the confidence interval. Yet the interval takes it further, emphasizing both our effect size estimate and the stability, or in this case, instability, of that estimate. In the next example, p equals 0.08. The effect size is just about the same as in the previous example. Yet for that example, p less than 0.05 and now p greater than 0.05. The increased instability reflected by a slightly wider interval means that now we would infer the null hypothesis as a reasonable possibility. Here's an example with a relatively large p-statistic. We're not surprised. Large p-statistic associated with an effect size estimate that suggests trivial effects. Yet note that the confidence interval also suggests maybe the real effect is not trivial. Some values in the interval correspond to a small but non-trivial effect. And here's the final example with another small p-statistic, p less than 0.001. This is one of my favorite examples because it clearly illustrates that while very small p-values of a p-statistic may indicate a large effect, that's not always the case. Remember that the p-statistic is based on both the size of the effect and the stability of our estimate of that effect. In this case, the effect size is trivial, but we have a very stable estimate. I consider this to potentially be an important and publication-worthy finding. Imagine past research of the same treatment had suggested a treatment effect because p less than 0.05. This follow-up study now states with 95% confidence that indeed there is a treatment effect, but it's trivial. The study focused on obtaining a very stable estimate of effect, something that is within the researcher's control, considering the long list of study elements that influence the confidence interval width. I believe a strong case could be made that publication decisions should put more emphasis on estimate stability
the width of the confidence interval, than on the value of the p-statistic. The closer I move this very narrow confidence interval to 0, the higher the value of the p-statistic. But how would that decrease the importance of our findings? And why should that influence publication decision? You may have surmised from my remarks that I perceive a gap between the promise of statistical inference and the practice of statistical inference. I'm not alone. Calls for changes to practice in my own discipline have been frequent, spanning years and decades. Two of the most prominent of these were commissioned by well-regarded professional organizations in which I hold memberships. In 1999, the American Psychological Association Task Force on Statistical Inference published a report entitled Statistical Methods in Psychology Journals. The report begins by acknowledging a controversy. In the light of continuing debate over the applications of significance testing in psychology journals, and then continues to make several recommendations, including a focus on effect sizes and the inclusion of confidence intervals. 20 years later, in 2019, the American Statistical Association convened a task force on statistical inference that published a statement on statistical significance and replicability just last year. I encourage you to read it. It is short, well worth the time. There's one paragraph to explain each of these summary statements. Now, I have touched on all of these a little bit in my talk, but perhaps this sentence in the paragraph about statistical thresholds best aligns with my motivations for the topic of this talk. P-values and statistical significance should be understood as assessments of observations or effects relative to sampling variation, and not necessarily as measures of practical significance. I recommend we modify our research language to put the focus on estimates of observed effects, accompanied by a discussion of the variability of these effects. Here again, I'm going to show you the p-statistics and confidence intervals from earlier examples very briefly, and I'm going to suggest possible phrases to describe each finding. Now, given my lack of familiarity with your instruments, I'm going to use a generic term, units, as a placeholder. The average effect for our treatment participants was an increase of 6.8 units. From this, we can infer with 95% confidence that the average effect of the treatment is substantial, between 5.8 and 7.8 units. Though we are 95% confident of a treatment effect with an observed average effect of 3.5 units, the high variability of the estimated effect from 0.3 to 6.7 units suggests the need for further research to confirm treatment value. Although we are not able to confirm at our chosen level of alpha 0.05 the treatment has an effect, our outcomes with these participants were encouraging, producing an estimated effect size of 3.4 units. We have planned additional study to determine if we can replicate a practical effect and to do so with greater precision. We consider the average treatment effect of 0.6 units too small to warrant recommending treatment implementation, though further study is needed to obtain a stable estimate of the treatment effect before we can rule out meaningful treatment efficacy. These study results confirm with 95% confidence that the average treatment effect is rather trivial, ranging from 0.5 to 0.7 units. It is one thing to change our own language. It is another to promote change within the discipline. In my own discipline, the APA task force was only created after many years of discussion, accompanied by many articles criticizing current practice. On the task force recommendation, many APA journals now require confidence intervals, but some still don't. Keep in mind, these recommendations were published over 20 years ago. The recent ASA task force was founded in more revolutionary soil. It was commissioned in response to the Journal of Basic and Applied Social Psychology announcing they would not print any manuscript that included a p-value or a confidence interval, in essence, disallowing statistical inference. There are less radical steps each of us can take to promote change. Here are a few. Changing the language in our own manuscripts is a first step. Requiring a focus on effect sizes and estimation variance when reviewing manuscripts is another. My third recommendation is a compromise, recognizing that manuscript publication in any discipline has a long tradition. We want publications, we want grant funding, so we must be realistic about that tradition. My recommendation is to combine accepted practice with additional language that can enhance the explanation of study outcomes. In short, do both. In my own teaching, I have students focus on the description of outcomes and the variability of estimates. But I also teach them about traditional hypothesis testing and p-values. At this point in the evolution of our disciplines, it might be considered malpractice to do otherwise. I conclude my remarks by returning to my opening remarks. I fear this talk could well come across as a speaker from another discipline who knows next to nothing about your practice telling you how it should be done. I hope that is not the vibe I presented. Here again are the goals I set for myself in preparing the talk: to reflect on practice, how it aligns with our philosophy, to talk about old topics in new ways, and to provide insights or ideas for students and new researchers. Thank you again for giving me the opportunity to work with such thoughtful and motivated students. Thank you for giving me this time today. I hope it will spark discussion, and I'm happy to be a part of that discussion anytime.
What we typically do, I'm waiting for Lisa to say.
Oh, sorry.
What we typically do is to take questions from the room if there are any, but we can also.
And I know you don't have much time, but I.
Oh, we got time yet? Yep.
Okay.
Any questions from our end here? And then if you don't mind, if you can repeat the questions so that people online can hear.
So oftentimes, as you kind of noted, we have people who respond to treatment or don't respond to treatment, and then a lot of in between. And I was wondering what your thoughts are on creating like binary groups to try to basically find out what are those predictors in determining, so what are those epsilon factors that are determining whether they are successful or not with the treatment, and how that sort of fits into this.
Yeah, so the question was about when you have individuals not responding to a treatment and those that do respond to a treatment. I mentioned that in terms of discovering that in your residual analysis of the type that I was talking about. And the question is, what about putting these into binary groups? And that actually falls under a term that I always think is misleading. It's called causal comparative, because it's not assessing cause, it's looking for potential causes. So you could do that binary as certainly as a first step. Alternatively, or in addition to that, you certainly can start introducing additional covariates into your model to see if, in fact, any of those are going to be good explanations for why you're finding those differences.
We have a question online from Kirana Tsapkini. Thank you for this illuminating talk. She says, is Monte Carlo simulations a better solution than p-values? And also, how do we improve estimate stability? Larger sample sizes or narrower and more homogeneous samples?
Okay, so I'm going to actually repeat the second part because my mind already started going with the first part about Monte Carlo studies as a means of inference instead of p-values. See, I use Monte Carlo studies in methodological research where we simulate. So you certainly, I don't know that they're two separate issues of p-values versus Monte Carlo studies, because you actually can have p-values in a Monte Carlo study. And certainly we use, I'm actually a non-parametric statistician by trade and practice and my primary interest. And so we do a lot of what I referenced today, randomization testing. And in those randomization tests, oftentimes the distribution is too overwhelming to be able to calculate all the exact probabilities. So we do Monte Carlo simulation as a selection of those. But even in that, we have p-values. So I'm really not sure if that is an alternative. I think maybe a supplement. as part of it. And what was the second part of the
So
question?
the second part, actually we have another question from Dorian Postina that is similar, so I'm going to ask both of them. The second part was, also, how do we improve estimate stability? Larger sample sizes or narrower and more homogeneous samples? And Dorian asks, besides increasing sample size, are there other approaches for reducing the estimated range of effect size?
Yeah, so is my screen still showing
Yeah.
it? So that was, going back here, let me go, because I went through this list pretty quickly. I think I just passed by it. There it is. I went through that list pretty quickly, so you probably didn't have a chance to look over. So the question is, how do we increase estimate stability? And that literally, by the way, when I teach, students who have had me in the past, those who have me now, we're just in some of my classes just now getting into inference, so they haven't seen it much. But when I teach, I have them write reports, and I make them focus on what they actually found in their study, because it amazes me, even in the research in my own discipline, how many pieces of research I can pick up, and the immediate jump is to inference, as opposed to focusing on the actual estimate of the effects that you got in your study, which, by the way, most of the time those estimates are statistically maximum likelihood estimates. That literally means it's our best guess. And so we should be focusing on those estimates first and foremost, and then we should be focusing on how stable is that estimate, and all of these speak to stability. So number of observations is the one we always think of, but do we have the extraneous variables that we could include because we have measures on those? Do we have those to include in their study and thus reduce the residuals and consequently narrow the confidence intervals? The mention in that question was on what about homogeneity? Homogeneity, I always think of internal and external validity as really a teeter-totter balancing act. So if you increase the homogeneity of the participants, you increase the estimate stability for your causal influences, but you have a smaller range of individuals you can then infer that to. But for my money, I always go with internal validity, because we can always replicate. Now, unfortunately, replication, which is one of the most powerful things we can do in our disciplines, tends to be a dirty word among a lot of publications, a lot of journals. They want to understand how is this different than something that's been done before. I wish it wasn't that way. That's another area in which I wish we would change things. But anyway, you can see here, making sure that you have very consistent treatment implementation. I imagine in your fields that often research is done in which you have different clinicians that are involved in the research. And that could potentially change the variability of treatment implementation. So all of these are stability influencers.
Question, I think you probably touched on this already, but just to clarify from my own mind, the sort of old school model of p-values is like, okay, your result is significant or not. We publish it if it's significant, or we discuss the results if it's significant and not if it's not. And I think the implication in your exposition here, right, is that you kind of reject that. You're not reject the binary nature of a p-value or the alpha threshold, but that you want to discuss the nature of the result regardless of where it falls.
Right, right. So my way of thinking about it, what I tried to show here, because both think of p-values as some measure of probability of the results, and what I do say is that idea, and I didn't repeat the question was about the binary nature of the p-value and moving away from that. But the idea of the binary nature of the p-value is actually required if you're going to do it as a probability. That was one of the things I tried to show. But what folk tend to try to do that I think we don't need to do is somehow combine in the p-value both that reject or not reject decision and some estimation of the effect size. What I try to do is take apart the p-value and say, this is the part that we're doing in terms of the probability, but here is how we can actually focus on that effect size. without trying to get it from the p-value. And if you look at my examples, I purposely have two p-values of 0.01 on totally opposite ends of the spectrum. And so using the exact same p-value as indicative of effect size, it could be very misleading. But we can get around that by focusing on these other things, on effect size and stability of estimates, yes.
I think you referred to it indirectly, but I'm wondering if you could say something about the use of the notion of trending effects.
Yeah.
Which is very common.
So yes, it is common. So you know, because you get that, if you get that 0.055, what do you do with that? You know, you fear that the journal is not going to publish it because of that 0.05, and that's where I wish practice would change and focus on stability. And so you say, well, at least this trended towards significance. But one question is, maybe it's running away from significance. I mean, what you literally don't know is if you were to get a little bit more stability to try to get that thing to be under 0.05, things could go in the other direction. And so your confidence interval, if you think of your confidence interval decreasing, it might show you with more confidence that you don't have that effect you were hoping for. Yeah.
So I think like that language, right, is I think people what they intend by that, maybe what they charitable interpretation, right, is that this is close to the threshold. That it seems silly to arbitrarily like reject a paper, for example, right? Like, you know, person A publishes P.049 and I publish 0.051. There's really no meaningful difference in the observed results.
Right.
Right. So it's kind of highlighting just the arbitrary.
Yes, I understand. That's in my discipline as well as yours. That's that idea that the statement was that, you know, you have this p-value that is right around 0.05 on one side or the other, and the idea of that binary decision seems disturbing. But my proposal today is to get around that by doing it in ways other than the p-value, since the p-value has so much wrapped in it.
Right.
Yeah.
Taking up on the point about trending that was brought up, how would dose-response relationship play into this? Like, you might find at the lowest level of the same treatment, the lowest dose of the same treatment, you have a p-value of 0.055, and as you increase the dose of the treatment, you're able to clearly show both increasing effect size as well as you know, a p-value that is below 0.05. And so would you then be justified to say that the results are trending towards showing that periodontal disease is you know, associated with cancer, and increasing dose of periodontal disease is showing this, and therefore, even though the lowest level of periodontal disease did not statistically significantly associate with cancer, because the odds ratio and the you know, confidence interval spanning 1.0, but this dose response relationship, can I say that, well, okay, we jump on the trending you know,
Sure.
terminology and say, oh, well, we are showing that it is.
Sure. So trying to quickly summarize for those that might be watching, the question is, if you find that, for instance, with the increase of a dose, or maybe even increasing some other factors of an intervention, it wouldn't even necessarily need to be a dose. And you find that when you do this, comparing it to past studies, that your p-value is actually decreasing, which maybe could lead you to talk about trend. My response to that, again, consistent with what I was trying to show today, is why would we want to do that? Why would we want to do that instead of looking? I mean, I think your answer might be because that's the reality of the journals. But that's why I suggest adding language. Because what you want to be able to do is to be able to say that the easier way for me to say that I'm getting a trending effect that the more I increase whatever my treatment is, the more effect I'm showing. I would really like to see that happening in terms of the effect size estimate increasing, dragging with it the tails of that confidence interval, which is what results in the p-value becoming smaller and smaller. But I would like to actually be showing those things. And then if you want to talk about this trend, you're talking about the trend in terms of actual effect estimates in view of how variable those effect estimates are, instead of talking in terms of a p-value that we could think of all sorts of examples where effect size goes down and your p-value still goes, your effect size goes down and your p-value goes up, or vice versa. We can think of those. So I would prefer, personally, to focus on those particular effects of interest.
We have a few more online.
Okay.
One is not a question but a comment from Lindsay Kaler, who you know.
Yes, I do know.
And she is now
Hi,
a
Lindsay.
professor at the University of Delaware.
Yes.
Thank you, she says. Thanks for a fabulous talk and for diligently leading this conversation that is so important to our field and others. We can all echo that. And then we have a question from Dorian Christina. Modern studies have many comparisons which require multiple comparison correction, usually done on p-values alone. Where does effect size stand on this process? Does multiple comparison correction need to take into account effect sizes in some form? Thank you.
Okay. Yeah, both effect size and estimate instability. So for any multiple comparison method in which you're adjusting and looking at adjusted p-values, there is a corresponding adjusted confidence interval for that. So the students like Lisa shaking her head because she knows that's what I teach. Lindsay back in Delaware is shaking her head because what we do is we look at, we recognize that you still have to have error control, and you control it for a family. And so if you control it for a family, you have to make adjustments. All the adjustments that are available for p-values are available for confidence intervals, allowing you to look at the effect and the stability of that effect.
Thank you very much. We have no more questions online. I suggest we...
I just have one, you seem kind of like you have a revolutionary point of view, I think, in the field of like the way we talk about studies and, you know, which studies get published. And I was just curious what your thoughts are on like the publication of null findings in an area like in a replication study, where I feel like it's not very appealing maybe to journals, but those null findings may actually play a part in the future of how you do research as well.
That's right. Not only that, so the statement was, what are my thoughts about null findings and the publication of those findings, because they may have implications for the future. They definitely do. I tried to give one example with a confidence interval where folk could have been studying and publishing because of p less than 0.05, but doing so without stability, and once we put stability, we find out it's a trivial effect. Beyond that, at the level of the journal, and at the level of how our fields advance. Do you have in your field a discussion ever of the file drawer problem? So the file drawer problem, of course, is the one where the P's that are greater than 0.05 get put in the file drawer and the others get sent in. That actually has, in my discipline, that actually has been studied by methodologists who have been able to estimate the bias level of effects based upon what's published versus what's not published. And so the field is getting the wrong impression. The American Statistical Association actually has been considering different ways to recommend publication. And one of the ways that they recommend, this would be tough to get it done, but is to judge all publications on the merits of the methodology and publish anything that has good methodology regardless of results, in order to remove the bias that comes in with that file drawer problem occurring. So.
It's like pre-registration, right? I mean, it'd be logic behind pre-registration, right? You register the
Yes, that
Study
is,
without any
right,
results.
that's right, yeah.
I just hope they're really short papers then. Not need to read a 40-page paper.
Exactly. I mean, none of this has good, clear answers.